Hello everyone. Today I want to show you how I do a so-called edge hardness testing. We are probably all familiar with the so-called Rockwell C hardness testing, which uses a machine like this, a Rockwell tester. You put the blade, in this case a box cutting blade, under it, lower the lever, and you will put a little indentation on the side and it will read a value. However, this test method has a few limitations. One of them being that you can only test flat parallel sides of a certain thickness because it uses 150 kilograms. And if we managed to put the edge of this blade perfectly parallel to the tester, well, even if we manage that, the weight would crush this edge. So what we are going to use, and what I use, is a so-called Micro Vickers tester. Vickers is another measurement scale, and it can be, I will show you that later, converted into Rockwell C. Okay, but the cool thing about it is it has very small weights, ranging from 10 grams to 1000 gram, and we are going to use a 25 gram load weight behind this. You can see it hopefully, yes, this little nose here, which is called the indenter, to apply a very tiny amount of force on the edge area and measure it. Now, that sounds all cool and good, right? But there's a very big problem with this, and that's the following. If this is the indenter, again, this little nose here, it's for all kinds of indentation-based hardness testing crucial that the surface of the test piece and the indenter are parallel. These little lines here mean parallelity in geometry terms. So this needs to be parallel, these two planes. Or if you imagine a vertical line like this, you need here and here 90 degrees. The ASTM protocol allows for plus minus 2 degrees, but actually I think that's a little much, so we will be much lower. Now, how do we achieve that? Again, with a flat surface, specimen like a blade, we could just put it under, measure, and be done. But how do we get this up, facing upwards and parallel? Now, this is how I do. Let me quickly focus. Okay, if we imagine a knife edge like this, right? The knife edge, a sharp knife edge, ideally has a diameter of less than 0.5 micron, much less actually if it's sharpened well. And this test machine ideally needs 30 micron of surface diameter of the edge, right? If red here is the surface diameter of the edge, to give an accurate reading. Actually, it's a little less than 30 micron, but I want to be on the safe side. So somehow we need to make this edge 30 microns wide, which is easy. Of course, we can just, in theory at least, rub it onto something until it gets wide enough. But we need to have it perfectly parallel, right? And we don't only have to have it parallel in a 2D way. All sides need to be perfectly square, as we say, 90 degrees. It cannot be off in any direction. It must be perfect. Okay, so how are we gonna do that? I show you, and what I'm about to show you is inspired by some other studies that have been conducted on machining knives, and yeah, this is my method, and I want to show you now. So the first thing we need to make sure of is that the apex of the edge, the apex is basically this line here. Here it's 0.5 micrometer or 30 micrometer, this is the apex. It needs to be parallel with the spine of the blade. And this is why I'm using a box cutter here. For once, there is no factory brand name on it. And secondly, it's very easy to work with because luckily this is parallel to this already. Of course, I measured it. It's difficult with one hand. I need a better tripod. Yes, but I wanted to make this video fast. It's parallel, okay? So that's the first problem we have eliminated with this blade. If we took a knife blade like this, and this is the only manufacturer, or not the only, this is a manufacturer which was okay of me showing this. If we have something like this, okay? It's much harder, or you basically can't align this properly without taking it on the milling machine and making a straight cut here, okay? So this is destructive testing, and then putting this straight line into the vise and doing what I'm about to show you now. And it's the same with here. Whatever edge you, or whatever blade you test, it's important that the spine for my method is flat, because now we're going to use this nifty device. This is, if you're not familiar, the so-called wicked edge knife sharpener. And usually a knife blade is put in like this, and you sharpen it from both sides with these diamond stones or files. Now, they also sell a so-called scissor sharpening adapter, so that if you had a scissor, you can put it in there like this and sharpen it. And the cool thing about this, basically everything about the Wicked Edge system, is it's very precise. They claim, and I've measured it with my angle cube, they really have an accuracy of 0.1 degrees. And this is crucial. Again, remember, we have up to 2 degrees of variance allowed by ASTM, but we want to go much, much more precise, because, you know, precision wins. And now I will quickly put you on my improvised tripod stand and show you what I'm about, what I am doing. Okay, perfect. Now, again, we have, I want to point this out again because it's very important. We have already determined that these two sides are parallel, okay? And I quickly make sure, yeah, it's focused. So, because this is a very, very thin blade, I have a little shim here that I use to put it in this clamp. And this clamp is perfectly, I'll show you this in a second. This clamp is perfectly in, it has square surfaces, okay? This is very important. It has square surfaces. And the next thing we need to do, we now want to go, that's our plan, with this diamond stone. Whoops. We want to make a shoulder that has 30 micron in diameter, because you remember this diameter of a normal edge, okay? This is way too small. This is less than 0.5 micrometers, so we need 30. So what we need to do is we need to file it down. But again, I'm repeating it again so you don't forget it. We need to be parallel. So we just can't go in here and file in some way. We need to make sure it's square. So how do we do that? The first thing we do, and I put you down here again while I set it up, and then I'll show you in detail. The first thing I do, I go here with this stone and make sure by eye, first only by eye, that it's square. I have already prepared it. Then I take, and I will soon show you up close, this little watchmaker's precision square, which as a funny story, I inherited it from my uncle, great uncle, who was a watchmaker. I will use this, and this side here, this plane here, you can see that this is parallel again, it's all squared up. I will put this against this plane and put it on the flat side of the blade, and then come with this and make sure it's square. So now I show you what I mean. And of course, you need to have, come on, focus, there we go. You need to have parallel flats on the blade. If we don't have them, well, not every blade can be tested. Most of them can, especially folding blades, because by design they need at least at the pivot some flats. If you see here the pivot, right, these need to be flat on parallel or the folding knife won't work. So yeah, and then we make sure it's light tight, which it is, okay? So now we have this 2D plane of parallelism covered. What we don't have covered yet is this side, because you could still be wiggling. So in order, and I put you back down. So in order to make sure this is not happening, I have this bigger vise here, and it's also squared up against this base. Here's a little oil, so it glides better, and it's also from sharpening. Okay, I have this little square, and then I can basically use this. Can you use this as a guide here? You can see here, this is a guide I can use. Yeah, and then I go up and down and sharpen that, or not sharpen actually, I dull it until I have this little step here created with you know, with around 30 micron diameter. Now this is around 100 micron already because I've tested this a few times and tried different things, but it's just for demonstration purposes. And then what we will do is I go up to 0.5 micron. This needs to be a mirror polished surface. This is very important because the indentation, you can imagine that if we make an indentation with this little knob here and use only 25 gram, this indentation will be very small in the diagonals. You will see it live later, but I just want to show you what it looks like. It has a pyramid-shaped diamond head, and this diamond head or cone will create an indentation that looks something about like a square or a diamond or an octahedron. You get the idea. And well, you can imagine if we take a look back at this surface here, if it would be rough, okay, and this is our diamond cone, and the rough surface macroscopically would look like this, and we hit the side of a hill here, if you will, okay, then the reading would be off, because on this side there would be less material to push aside, on this side more. It would most likely give us a softer reading than it really is, the material we are measuring. So it needs to be as flat as we can get it. And as smooth as we can get it. Flatness and smoothness are actually two different things. That's also something I want to get across with this video. We can have these two sides perfectly parallel, okay? But again, if the surface is something like this, microscopically, then you can imagine we won't get an accurate surface. So 0.5 micron or a polished surface is the standard. If you look at this, and excuse the fingerprints, this is a test block. You can see how polished that is, right? This is about the amount of polish we want for a good testing. And it's about, actually 0.5 micron is polished more than this. Okay, and I also I will in a separate video upload just a calibration with this, so just that you see that this machine is calibrated. This is the manual, by the way, really cool machine. So anyways, now again, I've pre-polished this a little. Now we can take it out. And again, this was the shim because this is so thin it would hold otherwise. Now we take this cute tiny little vise, isn't it cute? It's a precision vise used for microscopy. Yeah, but whatever. I'm not a native speaker. So, and we are going to mount it now in the testing machine. Now, of course, this vise and this surface are square. And again, you remember, these two sides are square. Yeah, you get it? Are square. So if you put the spine on the flat side, on the bottom of the vise, it will be square. Okay? And you see me touching the surface here of the probe. You shouldn't do that if you... Again, this is just for demonstrating how I do it. And the whole process takes about an hour, okay? So I don't want to bore you with a 1-hour video, but this is just how I do the specimen preparation mounting. So we have this here, okay? And it's very important, again I show you, that this is pushed down and parallel. Okay, so you can see here, this is riding. Let me show you that up close. This is sitting in this vise, okay? And you can see here, if I get this to focus, come on. You can see that there's a little shoulder cut in it, okay? It makes a little bit of a curve downwards. This is the plateau with about 100 micron, 30 micron minimum we cut. And yeah, in theory we could test, but it's critical that nothing is pushed around. And yeah, 25 gram maybe don't seem a lot, but even with the 10 gram load force, okay, it will be, you know, enough to push it out of line. And we are measuring amounts of 0.1 micron. Imagine that. That's a tenth of a thousandth of a millimeter. Okay, all metric. I don't even know how fine that is in inches, but it's a very, very small distance. So we need to fix this even better. And the way I do that is as follows. Where is my, yeah, there it is, my beloved Kent twist clamp. This is a precision clamp, and what we do first, and now I will talk about the measurement. Now I just loosely put this on here, okay, just loosely switch on the machine, and then what we need to do, yeah, and I will show you without the Kent clamp, because with the clamp I would need 2 hands to actually do it. You can see that this machine has this kind of revolver thingy here, okay? 2 microscopes and the indenter. And it works like this, or I should first start with something you maybe know better. A Rockwell test machine, once you put in the indenter, it gives you the reading right away on the display. Vickers works different. The indentation, which looks like this, and I will put a little, yeah, I will at this point of the video put visible a little screenshot of one. The indentation will be measured with the special measuring microscope we have. And I'm trying to show you that. Again, no cuts or anything. I just want to make sure you can see everything. Or, you know what, let me first find it so you have something to look at. And yeah, the test specimen preparation, by the way, is over now, so that you can see, you can leave now if you don't want to see how a Vickers test is performed. Now what we want to do, we want to line up this probe, the center of which is important, where we ground it flat. I have a little light shining down here, like an aiming laser, that will give a little reflection, so I will put that to focus. There we go. Again, now the surface you're about to see in the video, it's not really smooth because I touched it just with the diamond stone. But yeah, you can now see, I'm trying to bring that to your focus. You can see here, see this line, this is the actual edge. If you still can call something with that kind of diameter an edge. And if this, oh, there we go. If this was polished again, it would be just a white surface. And you can see also a little crosshair, right? And now you can see that moving, right? And these, basically the middle line where it crosses with the big line is the point of impact of the indenter. And once we have that indent made with these 2 lines, we need to touch both sides of the indentation twice, okay? And the display, and it will change depending on, these are microns, 12.9 micron, 12.8, 6. Okay, this is extremely fine. We measure the diagonals, both diagonals of these indentation. Okay, diagonal 1, diagonal 2, and then the machine automatically will calculate the Vickers value and it will be displayed here. I suggest that if you really want to see how a Vickers test is done, go down to the description of this video, and I've linked the paper there where the whole process is laid out, okay? And if you want to see some diagonal values, I have them on my Instagram. If there is interest for it, I can do a complete live test with a probe and everything. But yeah, as far as that, so once I have lined up that probe, that's the last thing I want to make sure. I will fix it with a cant clamp, and now you see I need to basically go in here with my hands and make sure it's tight. There is as an aftermarket, you could buy some fixing plates, but they're not ideal for knives, and they are also like, I don't know, $1,000-$2,000. So they have luckily pre-drilled holes here, so I can make a test plate, so I don't need this anymore. But it works perfect. It's yeah, because everything is square. So that's the last thing I want to show you before I end this video. It's very important if you fix it that, and this is possible. Oh, let me start this way. Here it must be perfectly light tight, no gaps or anything. So yeah, this is actually not perfect. 1 second, guys. There we go. So you can see everything is mounted square. Now, once we have lined up with that microscope, we need to go a little lower, and this will, and I will show a video of this at the end of this video. This goes down, tests it, dwells for a few seconds, which we can determine here. Then it goes back up, and then we take this very high magnification microscope and measure the indentation again with this little crosshair thingy. Alright, so this video, again, long video, 20 minutes now, over 20 minutes. The purpose of this was to show how I prepare the specimen for the testing. If you want to see a complete Vickers testing, which I would do now, which again would probably be at least a 10 if not 50 minutes video, let me know in the comments. I will be happy to do that because I think transparency is very important. But yeah, again, let me summarize what we have learned today, if you wanna say it that way. It's very important that the edge has enough diameter, around 30 micron, for a reliable indentation. It must be smooth, and most importantly of all, it must be perfectly parallel. That's the most critical thing. If it's not parallel, then you won't get an accurate reading, and that's something you don't want, of course. So you either have to machine it so that you can have it mounted square, or if you're lucky, like we are here with this kind of blade, you can directly go to test it. If you have a Vickers test, that is, these are very expensive. I'm very lucky I got it for a fantastic price. It's basically, it is factory new, but was unused for 3 decades. Then it got recalibrated, and now I'm lucky enough to own it. Still was pricey, but I think it's worth it to control my quality. And I have, if you've seen, I've been contacted by companies, bigger knife makers, and really big companies. And it's my big honor to test some blades for them, and yeah, well, we will see where this goes. I'm very happy that my test results are accepted, and because of that, I also wanted to share how I make this specimen preparation. Again, this is the Wicked Edge. It's very precise. There are several models. I have the very precise one, which allows even finer adjustments, and I use, of course, an angle cube and everything, and the angle cube is put on here, and then with a square, you can make sure it's parallel, all that stuff, all that good stuff you need to do to get an accurate result. Again, let me know if you want to see a complete test of the Vickers hardness value. Any further questions, I will leave again a link to a Vickers testing protocol in the description, as well as my contact info for my website, for the knives. If you want to buy one, or if you want to know more via the website, you can write me an email, and my Instagram is also there. Thank you very much for watching. If you want to have something tested, please let me know. Depending on the amount of work, I can either do it for free, or usually it's a lot of work. If I have to mill it, then I would have to charge something. Again, there are some companies doing this with me right now. If you are watching, thank you very much for your trust. I really appreciate it, and I'm glad to work with you. If there's anyone else out there, please let me know. And yeah, just one final disclaimer: I don't want to call anybody out or something. If you follow my Instagram, I have posted the hardness edge value of one of my favorite brands. Like I love their designs, they're awesome, but having a few knives of them now, some were, overheated at the edge, and yeah, I posted that in the hope that something will change, but nothing meant in a harmful way. But apart from that, I don't want to mention any manufacturers unless they want to, which in this case would be Kunwu Knives. They had me test something here, which I did, and very cool to work with you guys as well. So yeah, thank you very much for watching, and have a wonderful day. And again, please do not hesitate to reach out to me. Goodbye.